Hello everyone, welcome to Recitation number 9 of 11785 Spring 2020. Today we're going to talk about attention networks. Hopefully the first part of this is going to be a review of the lecture. So let's get started. So let's look at what we have done with RNN so far. So we have many-to-one. We have looked at many-to-one architecture and many-to-many architecture in our homework 3. So in part 1, we have an RNN classifier where we run the network through the entire input and only generate one label at the last time step, and we back propagate through this entire process. And in part 2, we dealt with speech recognition. So we wanted to generate a phoneme sequence from the speech utterances. So this problem, although we don't have a one-to-one time synchrony, we do have order correspondence. The order in which the phoneme appears in the speech and in our generated labels are always the same, and so each output corresponds to a small segment of the input speech utterance. So now let's look at some different tasks, such as the machine translation and image captioning and question answering. So for these problems, we notice that there is no such notion of order correspondence. For example, in machine translation, we might have different ordering of words in different languages. For example, if we have in some languages, the verb is usually the last word in a sentence. So to translate these languages back to English, we literally have to wait until the last word to know what to generate in English. So in these cases, we need a generative architecture, which is composed of two parts, an encoder and a decoder. So for the encoder, we run the input through the entire input, and we generate a hidden state, and we pass this to the decoder and let the decoder generate the outputs one at a time. So the decoder is essentially a conditional generator, which generates a label yt given the input sequence x1 through xt and y1, and also the previously generated outputs y1 through yt minus 1. So in deep learning, the decoder has to have access to some kind of encoding of the entire input sequence and the past states of the decoder. So the decoder is an RNN, so it has access to all the past states. So we now only need to focus on how to pass the encoding to the decoder. So here is the architecture that we use for homework 3 part 2. We're generating one hidden state at each time step, and we are using these hidden states for some downstream tasks. To change this to for our new task, we need to remove the output targets. We only need the last hidden state, because it's a function of all of the input and all of the past hidden states. So ideally, it's going to be an encoding of the entire input sequence. Now we could do this in many ways. So we could do it past this encoding only at the first time step. So we initialize the decoder hidden state using this encoding. But this is easily forgotten later, so we might want to do fix the encoding and pass it to the decoder at every time step. So this is our architecture. We get our encoding at the last time step of the encoder, and then we repeatedly pass this encoding to the output network. Now the problem with this architecture is that we're still using one fixed vector to encode this entire input sequence, and it's overloaded with information, and the earlier inputs tend to get forgotten. So it's really hard to train, and it's also hard for the decoder to focus because each time it's seeing this same coding. So what we want to do instead is maybe pass a more flexible input encoding at every time step. So what do you mean by flexible? It should be decided by the current decoder state. So intuitively, at each time step, the decoder should focus on a specific segment of the input to produce the current output. So put this in a formulation. We want to compute a time-varying input encoding that focuses on the part of input that matters to the current time step of the output. So this input encoding has to be a function of the decoder hidden state at the current time step and the encoder hidden states at every input time step. So from this, we can construct our general attention mechanism. So first, we construct a query Qi from decoder state Hi. So the Hi is the current decoder state, and the query represents the decoder's current interest. And then we construct a key Kj from the encoder state Hj for each input time step j. And then we calculate the attention score using the query and the key, and for each time step in the input. So this tells us how much at output time step I the decoder should focus on the jth input. And then we construct a value Vj from the encoder state Hj again. And then finally we construct the final encoding by compute the weighted sum of the values using the attention scores as weights. So this notion of queries, keys, and values are introduced by the paper Attention is All You Need. And notice that the keys and values are both generated from the hidden state Hj. But the key is what we use to compare with the query to generate a score, and we use the corresponding values V to combine to generate a final representation. So we kind of retrieve the values using the key. So it's important to understand this concept here. It helps you to understand how the attention works, and also helps to understand the multi-head attention that we are going to talk about later. So now we have our new network architecture. So we encode each element of the input into a vector, and for each time step we generate a query, we compute the scores, we combine them and get the context vector, and then we feed this context vector to the decoder RNN. So for the dot product attention, we basically use the current hidden state of decoder as the query, use the each hidden state of the encoder as both the key and values, and we simply compute the dot product of the query and the key, and over all time steps j, and we run that through a softmax layer, and we get our attention scores. So this is a very simple similarity calculation, but it works pretty well in practice. And one nice thing is that it doesn't introduce any new parameters to our model. And so the dot product attention essentially says that if the decoder should focus on the jth input, its hidden state should be similar to the encoder hidden state at time j. We're essentially forcing the network to learn to produce this kind of hidden states. And then we have the bilinear attention. So here the only difference is that we multiply the keys by a weight matrix before we do the dot product. So now the queries and the keys don't have to be in the same space. And we're introducing more parameters to the network. So now we have more trainable parameters, but we need more computation power. And then we have the additive attention, which the query and the key are multiplied by their own weight matrices and added together and then run through a nonlinearity and then multiplied by another set of weights. And then we do the softmax over all of the input time steps. And then we have the scale dot product attention. So this is what is used in the transformers. So the queries and keys and values are all generated by passing the hidden states through an entire MLP, and the attention is computed by computing the dot product of the queries and keys and scaled by the square root of the size of the hidden state. So the purpose of the scaling is to normalize for the size of the dot product, so that we don't saturate the gradient of the softmax. So essentially, because if we have a larger hidden state, our value of the dot product is going to be larger, so we need to compensate for that. So we can see that RNN-based attention is great, but it's impossible to parallelize the RNNs because we have to compute the outputs one at a time. We have to use the previous hidden state to compute the current hidden state. So there's this dependency that we cannot bypass, and the RNNs also have problems dealing with long-term dependencies, even with LSTMs. So maybe this is why we're going to introduce our new architecture called the transformer. So they were introduced in 2017. The paper's name is "Attention is All You Need." So it's a revolutionary sequence-to-sequence architecture, not just for machine translation these days. It's becoming the state of art for many of the sequence-to-sequence tasks. And so they completely removed the ERNs, and they just use the self-attention to capture the dependencies across the sequences. So here, this is the encoder, which uses multi-head attention. Then the bottom part is the decoder, which also only uses attention. And their claim is that, unlike in RNNs, the path of one word in an input sequence to one word in an output sequence is much shorter, because in an RNN we will have to run through the entire input before we generate an output. So this architecture lets the encoder and decoder see the entire sequence at once, and it also allows more parallelism than the RNNs, which we can see for obvious reasons. So one key component of the transformer is multi-head attention. So attention can be understood as a way of computing the relevance of a set of values based on the keys and queries. So in multi-head attention, we just apply this mechanism multiple times. We have multiple sets of weights for each attention head, and each head can now focus on different parts of the input, and they probably have different purposes. So the encoder of the transformer use self-attention to compute the recitation of the input. So it is the multi-head attention that we talked about before. It's just that the keys, queries, and values are all computed from the input embedding. And we also add residual connections between the multi-head attention blocks and the feed-forward network. And one thing to notice is that for transformers, since we're not using RNNs anymore, we need to give the network some kind of notion of position. So we're adding this positional encoding to the input embedding to distinguish, for example, the same word at the first time step and the same word at the last time step. So without these positional encodings, a sentence like I like 11.785 more than 10.707 will be identical to the output for I like 10.707 more than 11.785. So we don't want that to happen. So, and then finally, this this block of transformer encoder is repeated 6 times. So for the decoder, it's very similar to the encoder. We also had this positional encoding and masked multi-head attention. So why is it masked? So when in training, when we try to compute the next output, we need to mask the future output. Other than that, it's the same as the encoder. And here, the keys and values are passed in from the encoder, and the query is constructed from the decoder representation of the output. So this is similar to what we've seen in the RNN architecture, and then there are these skip connections. So finally, we run through linear and softmax to produce the final output probabilities. So we're looking at the big picture here. The input is added by a positional encoding, and then we run this through the multi-head self-attention, and we normalize and feed that to a feed-forward neural network, and we get the keys and queries to be used by the decoder. So for the decoder, we're also adding the positional encoding. We run this through masked multi-head attention, which masks the future outputs, and to generate the queries. So the queries come from the decoder, and the keys and values come from the encoder. We run through another multi-head attention and a feed-forward neural network, and then the linear network and the softmax to generate the output probabilities. Yeah, so for a more detailed explanation, you can go to this link. It's got a nice explanation of the transformer. So, yeah.
Okay, for the second part of this recitation, we will walk through a simple sequence-to-sequence model. This is just a toy example. In the homework 4, you may want to use a much more complicated model. We will have more details for homework 4 in the following recitations. As you can see, we just use the same task as the recitation 8, which is predicting the pronunciation of English word given its spelling. So the input is a sequence of letters, and the output is a sequence of phonemes. Notice that we introduced two special tokens here. The first one is the start of the sentence. The second one is the end of the sentence. Every target sequence is prepended with the start of the sentence and appended with the end of the sentence. This is necessary for the decoder to predict the first token and the end of the sequence. So in this code snippet, we just create some toy dataset, and we also have the vocabulary for the letters and vocabulary for the phonemes. Then we have to do some pre-processing for our data. As usual, we will convert our data to the tensor first, and we have to remember at the start of the sentence and the end of the sentence into our target sequence. Then we will get the raw length of x and the raw length of y, which is prepared for the masks we will use in the following part. Since x and y have variable lengths of sequence, we need to pad them using the pad sequence function. Notice here, the parameter batch first is set as default, which is false. If you remember in the recitation 8, we set the batch first for y as true because of the usage of the CTC loss. But this time, we don't have the CTC loss, so we just use the default setting of the pad sequence. For the whole model, we will have three parts. The first part is encoder, and the second part is attention. The third part is a decoder. Let's start with the encoder part. Actually, the encoder part is the same with last CTC recitation. We just use a one-layer bidirectional LSTM. So in the initialization, we just initialize a simple bidirectional LSTM. And notice here, the default value for batch first for LSTM is false, which is consistent with our preprocessing. And because we set the bidirectional to true, so if we want to get a result of dimension of hidden size, we have to set this parameter to hidden size divided by 2. And for the forward function for the encoder, it's the same with the last recitation. The only difference is that we have to also return the final states of the LSTM, because we need it to determine the initial states of the encoder. And also, of course, we have the encoded input as our return value for the following operations. And the second part is the attention part. We just implement a easiest attention version, which is a dot product attention. And the dot product attention don't have any parameters, so we don't have any code in the initialization function. And then let's go through the implementation of this attention step by step. We also have a very detailed comments for each step, for the shapes of each step. And the input for the forward function are the query, context, and the length. The query is from one time step in the encoder, and the context is the encoded input sequence which we get from the encoder. And we also pass in the length of the input sequences for creating the masks. The return value are the attended source context and also the attention vectors. But the attention vectors here are just returned for visualization. You may also want to visualize the attention matrix in the homework, because a well-trained encoder-decoder network will have a very clear diagonal-like picture. So first, we will use the BMM, where BMM stands for the batch matrix multiplication. We use the BMM to get the attention weights. And the unsqueeze and squeeze function here are just to make the dimension correct to make sure we can use the BMM correctly. And second, we want to mask out the padding tokens in the context because the padding tokens actually don't make any sense. We utilize the broadcasting here. The position larger than the length of the sequence will be marked as true, and we will set all of these true positions to negative infinity, which means we will ignore all of those true positions. And then we will do the normalization across the sequence length dimension using softmax. That is why we set the dimension equals to 1 here. And for the output, we do the BMM again to get the attention weighted sum of context. And also the unsqueeze and squeeze function here is just to make sure we can use the BMM correctly and keep the dimension we want. So we will return the attention weighted sum of context vectors as out, and also the attention matrix for the visualization. And the third part is the decoder part. The decoder will take in the token of the current time step and predict the token for next time step, because it just processes one token at a time step. So we can just use the LSTM cell instead of the LSTM here. In the forward function, we basically do two things. The first one is to compute the hidden state for the current token using LSTM cell. And the second thing is that we will use the hidden state we get from the LSTM cell and the context we get from the encoder to compute the attention, which is this line of the code. And then we will feed the concatenation of the hidden state and the attended representation into the linear layer to get the final output. Notice that we will also need to return the new state here because it will be fed into the next time step as the initial hidden states. So the new state will be the parameter state here, and the state will be passed into the LSTM cell to be the initial hidden states. And also the attention matrix here is just returned for the visualization. After creating our model, we are gonna step into the training logistics. So actually for this task, we can treat this task as a classification task. So we just use the cross entropy loss here. But in each batch, we have the sequences of different lengths. Therefore, we have some padding tokens in the end of our sequences. We need to ignore these padding tokens when we compute the loss. There are many ways to do so, but in this recitation, I just set the reduction for the cross entropy loss to sum, and the default value of this reduction is min. And after we set this reduction to sum, we will manually do the average afterwards. We just sum up the loss for the tokens that are we just sum up the loss for the real tokens that are not padding tokens and divided the number of the real tokens. Also, notice that for the optimizer, because we have two parts of the model, the encoder part and the decoder part, we have to include all of our parameters in these two models into the optimizer. So we will gonna work into the for loop for the training, and I just set 100 epochs for this training process. The first step is that we use the encoder to get the context and the state. Remember that we have to convert the context to the batch first, because when we implement the decoder and when we implement the attention, we assume that the input is the batch first. So we have to convert the context dimension into the batch first. And then we will go into the decoder part. So the basic idea of the decoder is using the current time step token to predict the token in the next time step. So we want to make sure the token for next step is in the valid range of labels. That is why we use I plus 1 here. Like we will iterate the sequence length. Actually, we will iterate through the time steps here, and then we will get the output and the states and the attention from the decoder. And then we want to mask off the sequences that haven't ended. So we only want to compute the loss for the real tokens. So active here is actually a mask. And we want to use this active mask to filter the output and the target sequence to compute the loss. Just remember that the loss is just summation of all tokens. So we want to divide the loss by the number of real tokens to get the average loss. And then just similar with the previous recitation. And the next part is a visualization of the loss and the attention. It's just some yeah, you have many ways to do the visualization, and basically it just use some package of the plot, and then let's see the output of this visualization. So these are just the attention matrix for each word. The x-axis is the input and the y-axis is the output. We can see that it doesn't work very well here, but because it's just a toy example. But I suggest you implement the visualization in your homework because the visualization will help you a lot with the debugging. And the last part of this recitation is the decoding part. You are not allowed to use any third-party package to do the decoding in your homework. Here we just show the simplest greedy decoding. For each time step, we just pick the token with highest probability. You may want to use beam search in the homework, but I suggest you start with the greedy search first, and after getting some reasonable results, you may want to try to switch to the beam search. Here we just create some toy example, and let's run it first. Yeah. So the basic idea of the decoding is pretty similar with the training process. We just use the encoder and the decoder to get the results. But here is one thing to notice that besides, so the stop conditions here, besides we use the end of the sentence. We have also need to include a restriction for the sequence length, or you may end in a infinite loop. And other step is just similar with the training part. The result here we can see is not really well, and it actually doesn't make any sense, but this is just a toy example, right? Yeah, and so this is all for today's recitation. If you have any question related to the recitation, feel free to post the questions to the piazza, and good luck for the homework.